Alright, so in this video we're going to look at the elastic potential energy that is stored in an object, which remember is 1/2 kx squared, and how that converts to kinetic energy, or 1/2 mv squared. Right? So again, just the law of conservation of energy. So let's go ahead and look at this simulation. So I've done a couple of things to the simulation to kind of eliminate some variables. So I've set the friction of the spring to 0. I've also set gravity equal to 0 so that it's not, we're not dealing with any gravitational potential energy. So we can imagine this is sort of sitting on the side, oscillating on a frictionless table when we have gravity set to nothing. And I'll kind of show an example of that in a different orientation in a second. So if we take a mass and I put it onto the spring, right, and if I just hang it on there, because there's no gravity, it's not pulling the spring anywhere, right, because I set gravity equal to 0. But what I'm going to do is I'm actually going to pull the spring, right? So if I then move the spring, stretch the spring out, I have stored some elastic potential energy that's relative to the spring constant of the spring, the springiness of the spring, and how far I stretch it. Now, when I release it, it should then start to move back to its original position. So if I let it go, it starts to move back towards its original position, gaining kinetic energy. And because of momentum, it's actually going to move through the position, like the axes here, where x equals 0, where there was no displacement, and go past it, and then it starts to store elastic potential energy here because we're compressing the spring by some distance, and then it increases its velocity in this direction, and then so on and so forth. But again, the energy is conserved the entire time. So let's look at how we might calculate a problem like that. So I'm actually going to show this so we can ignore gravity altogether. Let's put it on the spring on its side instead and say that this is a frictionless surface here. So I put the spring on its side, and this is its natural position. So this is where x would be equal to 0, right? Then I were to pull on it like I did with the mass, and I'm going to stretch it out some distance x beyond there, right? So I have added some elastic potential energy, which is equivalent to 1/2 kx squared, right? Now let me kind of come up with some numbers. Let's say that k is 5 newtons per meter, so that's 5 newtons to a force to stretch the spring by 1 meter, and that's the spring constant. And let's just say I stretch it in x of 2 meters. Right? Now, once I release it, this object, it's going to start to move back in this direction. Right now I've pulled it and I'm sort of holding it here, and I release, and it starts to move back in this direction, increasing its velocity. So at this position, what will happen is it will revert back here. It will have some velocity in this direction, and it will have kinetic energy, which was equivalent to the stored elastic potential energy that I had here. Right? So in order to actually solve this problem, if we can figure out how fast it would be going right here, we need to know the mass. So let me just make up a mass. Let me say it's 3 kilograms. Right? So I can just set the elastic potential energy here equal to the kinetic energy the object would have here. So 1/2 mv squared is equal to 1/2 kx squared. So my 1/2s cancel, and I get that v squared is equal to k, which is 5, times 2 squared, which is 4, all over mass, which is 3. So 20 over 3, which is 6.67. And then take the square root of that. So I get that it's going 2.58 meters per second right here. Now, as it goes past it, as it goes this direction, now the direction of the force changes, right? Because we're trying to compress the spring, so the spring is pushing back in this direction. So it actually causes it to decelerate and slow down until it reaches some other change in x, which would be equivalent to 2 meters in this direction, right? So this would be my x from here to here would be 2 meters again, causing it to slow down. And so then here, the velocity would be 0. It comes to a stop, right? So now all the kinetic energy is gone, and I have regained all of that elastic potential energy here. All right, and again, just by knowing the position or the change in x, we could at any point figure out what the change in elastic potential energy is and set that equal to the kinetic energy. All right. Now, I just want to point out the graphs again. So if we were to look at, say, a graph of kinetic energy versus elastic potential energy in this situation, let's say that this is 0 and this is positive x and this is negative x. And on this axis I have u, which is my elastic potential energy. And over here I have kinetic energy, and this is where it's 0, and I have negative x and positive x, right? Now, we know as x changes, the velocity is going to change, and velocity is actually squared. So, and over here, x is squared. So both of these are going to look parabolic, but we have to see how they're going to appear. So at position 0 is when the kinetic energy is the greatest, whereas at position 0 over here is where the elastic potential energy is 0. And then it increases as you get further away. So we're actually going to have graphs that look like this, and then this graph would look like this. All right, so make sure that you can both calculate but also roughly interpret the graphs of potential energy and kinetic energy relative to the displacement of the spring.